properties of the photon rings first from Alejandro, who's in Princeton now, next year in Los Alamos, and the year after that in Wake Forest, right? Yeah, Wake Forest, as a faculty member. So please, Alejandro.
Thank you. Is testing GR? Can you hear me? Cool. Okay. Thank you. Thanks to the organizer for this lovely invitation. Yeah, I come from a very different world, so bear with me, and then please feel free to ask me any type of questions. So I'm gonna circle back with the topic Daniel Meyerson introduced this morning. So I'm going to show some of those details for observational properties of this type of images. And my talk have changed 3 times already since this morning, so that's the number of talks I already attended. So I have added a little bit and modified my talk. So this is the first time technically I'm giving this sort of talk because I changed it so much now. Okay, so I'm gonna talk about black hole images and black hole movies. That's something we want to do eventually. So just a collection of images will make the movie. And here, even though we cannot see it very good because of the light, it's okay. It's okay, Nick. Okay, it's not okay. But then the idea, thank you, is that here I have color code in this simulation, greenish, bluish. One of the contributions that Daniel mentioned is this is the direct image. I'm gonna go in some detail. Then in orange, the n=1, photons that went an extra half turn around the black hole, and then here in white, n=2, and so on and so forth. This is the layer structure that Daniel mentioned. Thank you. You can put the lights on. Thank you. Okay, so let me just start by reviewing a little bit, or just mentioning why do we want to use images, or what Helvi was talking about, numerical relativity, or even what Paolo will talk about later, about like testing gravity in the string regime, where actually the gravitational interactions are both strong and dynamical. And I want to always, I like to start my talks like this because, yes, we want to test GR. GR is it's my favorite theory of gravity, but then we know it's not necessarily the ultimate solution. And actually, one of the key fundamental ingredients or properties of GR, and it's not necessarily unique to GR, but other theories of gravity, is that this strong gravity regime, or like this extreme gravity regime, we don't know exactly where it starts, meaning that we don't know exactly where these non-dynamical effects are going to be important. In Newtonian dynamics, we can certainly have a gravitational potential that is very large, but then the key distinction with, let's say, Newtonian gravity is that you can have definitely potentials that are very, very massive, like a strong gravity in some sense, but it's qualitatively equal to weak gravity. So there is nothing qualitatively different when you just change the potential of a Newtonian gravity. In GR, that's not the case. So in principle, we don't have a universal criteria to know when these nonlinear effects are going to be relevant. And that's why it's interesting to find them in as many systems as we can, even in the electromagnetic or the gravitational sector. Now, the point, and then what we want to connect is like, okay, what can we learn about this sort of fundamental physics from future observation? And as Helvi was alluding also in the gravitational spectrum, we have learned a lot. We have a lot of events in the strong gravity also regime, but it's because in GR, because of the unique properties, if GR holds, then we won't be able to learn new fundamental physics from just observing better black holes, or either in the electromagnetic sector or in the gravitational wave sector, because of the uniqueness properties. So in the sense, you won't find anything like it's sort of relevantly different or new. What we can indeed do is like actually learn more about fundamental astrophysics. We can do black hole population, how black holes start, how galaxies are forming, but in some sense fundamental, and this for the context of this type of conference that we're attending today, the questions are like more, okay, does gravity respect Lorentz symmetry and so on and so forth? Like, and we can, is cosmic censorship preserved? What about dark matter? How gravitational waves, for instance, propagate on a cosmological scale? Or actually, do we have more degrees of freedom, more polarization? So in some sense, if GR holds, nothing like this we will be able to observe just because we have better data. So let's keep that sort of in mind. So it will be nice, and we actually expect that GR is not the ultimate theory, so we want to explore all these questions. And then, of course, there are more things. Now, I'm going to just start focusing for the rest of the talk on just electromagnetic probes. And that one, in that sense, the only thing we're measuring about the theory is just the conservative part of the theory, and that means just the metric. So in principle, we are just testing how photons move in that particular background, how they get transported to observer, and then they create these images. Through gravitational waves and then numerical relativity and all that we help you also discuss, we will be able to see the dissipative part of the theory. But so from now on, I can just focus on these simple questions, or more simple questions, which are, all black holes are the same? Do they have horizons? And are they described by the Kerr solution in particular? So I'm going to focus on this sort of null tests, and in particular because of what Daniel also mentioned, many metrics in our theories of gravity, no, you actually don't even have don't need to have a theory. You can just you can write a metric, then you can derive these photons rings, you can produce images without necessarily having a theory, because we are just testing the conservative part of the theories, and that's something we can do. So it's gonna be always a null test of gravity, meaning that you think something, you observe it, and now you check if GR is okay with that. Then the dissipation and all that. So in that sense, the gravitational sector is much richer, okay? Bless you. Good. Okay, so now, how can we observe black holes? And in principle, there are just at least two venues. This is what I have been alluding so far because of their structure. One is because of the astrophysics. Everything that's around the black hole, we will infer the properties of the black hole just by observing light that's been emitted, or neutrinos, or any other of these messengers, or because of their geometric structure. But as I said in this talk, I'm just gonna focus on the astrophysics sector, meaning in the electromagnetic sector of this type of probes. And it's actually quite hard. I don't know if you notice here, there is a black cat. So that's one of the things. It's actually even very, very complicated to do. Good. So I don't know if you have ever seen this picture. And again, Daniel was mentioning, and you look at this and you say, okay, as Daniel was saying, well, can you do better? How will be the high resolution image look like? But in fact, this even like blurry image, has a lot of information already. So for example, it has this sort of Donna. You see this brightness asymmetry. Also has a flux depression that we can measure, and we know it's actually the background. We don't have a very dynamical range, so we know this is actually not no light. In some sense, there is some light, but then because of the resolution of the instrument, we know there is like a 10% floor. Because even if you have a black hole that has material, the material here will emit. So even if there is a black hole, you still have something to see here. And that's what Daniel was also alluding. We want to know more about like this thing, inner shadow, which is not necessarily the black hole. And then also connected to some of the questions this morning, if you know something about the distance of the source, then you just measure this scale, and then you know it's consistent at least with GR in some sense. The scale of this is consistent to having a black hole. So we have learned a lot of things from this image, this blurry image. And then the natural question, and the thing that we're here today concerned, is how can we use this type of measurements to study strong gravity phenomena? And it's actually, there has been a lot of discussion on this, because whenever you do any electromagnetic probes like that, you have two ingredients. You have the space-time, pick your favorite theory, plus the astrophysics. So as you see, like, trivially, the electromagnetic sector is actually much nicer, because all of these, well, this is still reflecting, but don't look at that, it's just this bit in the gravitational sector. So our systematics and issues, if you have your best theory of gravity, you know how to solve it in a computer, well, in principle, just solve it, get the observable. Whereas here, you have this complication, and that's why it's so complicated. And that's why, in principle, testing, and this is one of the key points of my talk, yes, we can do this type of test, but it's extremely challenging, and I want to remind everybody about how important it is to know something about the astrophysics, but in principle, how we can use that leverage. Because in the first place, it's not that we don't like the astrophysics. We do need something to be around to emit photons or whatever around the black holes. Otherwise, we won't see it. Yes? So here, we can make it as precise as we want in some sense, but think about if you make a diagram of curvature versus like a potential, M over R, and curvature put Ricci or Kretschmann. I'm talking about this region where like potentials are like sort of large and curvature could be potentially large. Well, if in this diagram, For supermassive black hole, that's absolutely true. But also we can see in the electromagnetic sector X-ray mass binaries, where you have a solar mass black hole with a star that is emitting. And then these photons are actually at the, let's say if you want, 6M. So this is sort of like a strong gravity. And you can measure electromagnetic things for neutron stars or like, as I said, X-ray binaries. Now that's a good point. And thank you, because I was about to remember. So in this diagram that I cannot make by hand just based on this question, if you write here like a sort of curvature versus like m/r type, yeah, this is what I mean by strong gravity in some sense. Here things will be dynamical, so curvatures are changing, the potential is changing because of that. But you are absolutely right. Sagittarius A star on M87 will be here, where the curvature is low and the potential is still large. Now, in that sense, because of the potential, we can still think this is interesting. But now connecting also to that question is, this sector is invisible today to the electromagnetic probes that we have, gravitational waves. LIGO is just observing this regime. GR also has a uniqueness property in some sense, because the black holes that are here should be of the same class of the ones that are here. So that's something I can also test here. So currently, through gravitational waves, we don't have access to these large potentials, like these kinds of monsters. So there could be something where the theory just changes. It's likely, I don't know, but then that's why. Now in the future, as Helvi alluded, Lisa will be able to store also this regime. But that will take until 2037, best case scenario, okay? So these are probes that we have for these big monsters. Thank you. More questions? Good. Okay, so this slide is about to show you in a very simple example why these tests are so complicated to disentangle these two ingredients, the space-time and the astrophysics. So here I have general relativity, and then I have spherically symmetric, is Schwarzschild, with Bondi accretion, material just going in, falling, spherically collapsing into the black hole, and then we take an image of that. So this is the result. Now, I'm doing this because here my astrophysics is quite simple. I just want to know how the profile is decay as a function of R. This is just a model for the astrophysics. And then my astrophysics parameter will be this alpha, okay? Now, if you have your theory of gravity, and then you can change this alpha and then produce different type of images, this is sort of like a toy model of what like the Event Horizon Telescope collaboration is doing. They are doing the very hard problem, but this is just a toy problem. So imagine you can compute your images. So from your images, you can compute a characteristic radius. I'll define this in a second. Actually here, it's just you just compute like the second moment of the image. So you compute your image, you compute this thing, and you know the answer, you know where this critical radius is, or the black hole shadow, and then you have a calibration parameter. So you can repeat this analysis for many astrophysics. This guy will change, you can fix the background, but then the characteristics, since it depends on the intensity of the image, will change a little bit. Then you can infer that, you have that calibration parameter, and now you can infer the thing that we in principle don't know. So this is more or less, in a nutshell, in a toy example, what would be the game if we take an image? You have a library of simulations that you know for your best theory of gravity. You have this alpha parameter, it will be a posterior. And now you take an image, so you know how to compute this from the intensity of the image. You can infer the critical parameter. So this is more or less the game. So again, in this very simple example, your astrophysics, you can compute a calibration parameter, because in your simulations you have access to the critical curve, and now when you see data, you do the opposite. You just use your posterior here, you know this characteristic, you just infer from the image, and then you do that, okay? So this is a very simple example. We don't have to know more than this. So now let me think about other theory, for example, one that Helvi also briefly mentioned. Before going to that, now you have this calibration parameter as a function of this alpha, my astrophysics, and then it has a particular shape. Okay. Now, let's go to another theory of gravity, scalar Gauss-Bonnet. The details here don't matter, it's a quadratic theory of gravity. And as you can see, first of all, it's quite similar to the other image. And now, let's go here, and then I say, okay, I have this coupling parameter. When I'm 0, I am in GR. I can also do a parametrization of the metric. Remember, I'm just testing the conservative part of the theory. 0 is GR, And then if I change this parameter, it's not GR. But then this is, again, no theory necessarily. Here there is sort of a theory. And this is more or less typically the result. What you see is that you change your astrophysics, your observable is changing quite drastically. The effects of changing the space-time are subdominant even in this simple toy model. So this is one of my key points of this talk. You can do this, and then depending how wild you want to go in this, this is what Daniel also was mentioning, if you crank up these parameters, then your deviations start being significant. But the key point of this work that we did is, one of the, is again to draw the attention that the effects typically in these sort of observables of changing your space-time are subdominant to changing your astrophysics. In the sense, oh no, the profile does, because this depends on the astrophysics, like how is the material, the plasma, the emissivity changing as a function of radius, for example. You say 6, then you get this, but you say it's 8, you change quite drastically, okay? So that's why it's so tricky to test general relativity with this type of probes in a nutshell. This is again a toy model, but then if you put more parameters, then the generality gets even wilder and it gets more complicated. Yes? It doesn't matter for the purpose of here. In this case, as I said, for this particular example, we have a scalar Gauss-Bonnet as quadratic gravity is coupled through a parameter that is a coupling parameter. And yeah. But here, as I said, A1 is a bumpy parameter. It's called like, oh, I lost my chalk. Oh, there are many here. So imagine you have your, oof, this is not the good chalk. Do we have the, okay, GTT, let's say you have your metric and then you can start parameterizing it in terms of these bumpy parameters, A1. This is a particular parameterization by Retsola, Shirenko, and Konoplia. But then you can start doing like, I don't know, I want it to be modified like this, or this is actually not how that modification goes. But then you can start adding modifications in this sense. It doesn't matter. You just choose your favorite parameterization. When this is 0, you recover a GR solution, Schwarzschild or Kerr. But here is just not even a theory,
but
okay?
I thought that A1 and A2 are determined by the solution to the equations of motion.
So again, just to, thank you, just to clarify what I was saying. If you choose your favorite theory of gravity, you have an action, then you might derive your solution. That's something you can do, for example, in scalar Gauss-Bonnet. And then you end up with a solution that depends on the coupling parameter. Another approach, which will be, you don't have a theory, which is what other people are also approaching, is you start with a GR solution, Schwarzschild or Kerr, and just add in Paolo even has his parameterization. You just choose your own way to parameterize this, and now you don't have a theory.
Mm-hmm. Okay.
Cool. Yes? So, yeah, this is, now we're collaborating,
Yeah.
yes, yes.
So if instead of a spherical accretion you consider a more realistic model of accretion, it's going to get worse.
Yes. So that was one of our conjectures. Yeah, that's exact. So even in this simple scenario, it's quite challenging to already do it. Of course, as soon as you put an astrophysics like magnetohydrodynamics, you put the magnetic
Or
field,
even just a disk accretion is going to get worse.
it's going to get worse in principle. Yeah. And some people have repeated this in more sophisticated complex. So, but yeah, yes. So that's it. Yeah. Yes, in some sense, there is no way why you do this, and then you do the complicated to the reality, and it's easier to disentangle them. Yes, thank you. Good. Okay. So now let's come back to what, whoa, that looks personal. Okay, so now let's go back to the story of the photon shell. And it's because everything now that I'm going to say until I tell you that I'm not doing it again is within general relativity, just the Kerr metric. As I said, I'm interested in a Kerr like, well, don't fall asleep, that's the only risk. So the idea is that it's just related to the Kerr geometry. So in Kerr, and this, as I said, it might not be a property of just the Kerr solution, but if there is a region in the space-time where you can trap photons, and here, and I connect this back at the end of my talk, the trapping is unstable. So you can indeed trap photons, and it's just in a region. If you're in Schwarzschild, it's like a particular radius. As soon as we have spin, this develops into something that is called the photon shell. Okay, so what we're gonna see here is there is a black hole here, the observer is at 0 degrees, and now there will be material, and we're gonna count, this is what Daniel also explained this morning, n equals 0 is how many times you cross the equatorial. You could choose any other plane, but here is just a labeling. Whenever you cross the equatorial plane, you will get to an image. So These are photons that just cross the equatorial one, and as you can see here, they will form an image. So this is more or less what the IPHT is actually we see. Now if we blur it, it will look like the donut that I showed you a few slides before. Now, as you can see, these are actually lens photons. They are, as you saw, like there is still strong gravity in some sense. But this is the direct image, which in some sense can also be considered weak lensing. And I'll mention why is this the case. But as you can see here, it depends a lot of the details of the astrophysics. And this connects to Paolo's question this morning. If you know what's the astrophysics, so maybe you can test GR in this way. Because you know everything about it. Now the thing that you know less is the geometry. Now, in this counting, there will be photons that actually will make an extra half turn, so they will cross twice the equatorial plane in this sort of labeling. And now this is the key part. They don't appear anywhere else in the image. They will appear in a region that is, in this context, it's going to be called n=1, or the first photon ring. And as you can see already, it's quite constrained. It's not anywhere. And it doesn't look much now that the astrophysics is there, but the astrophysics is still here. Now you go to n=2 or n=infinity, there will all these photons. But the key part is that the characteristic of this image in care are going to be controlled by 3 parameters. And we are already seeing one of those here. One is a sort of like a critical parameter, a Lyapunov exponent, because your image is like a mirror image of the previous one, but demagnified. You can turn off the lights. I think that was enough for the simulation. Thank you. So one of these the key parameters. Now, there is another one. It's subtle to see here, but also your image got rotated. And remember I told you this is the n=1 will be photons that make an extra half turn around the black hole. There will also be a time delay because the photon took longer to get to the observer. So this is one of the key points of Daniel's talk and my talk is like, in care at least, or maybe this is also genetic to other theories, this will depend on the properties of the black hole. Remarkably, and I'll come back to this guy is very insensitive to the spin. You have a Schwarzschild black hole, this extra time is 15 m in units of m. You have a spin of close to 1, it's still like close 16 or something like that. So this is very sensitive just to the mass. Yes, Paolo? He wants to, yeah.
So I was expecting that photons turning around would have more chances to interact with the matter around the black hole. Is this taken into account in this simulation?
Yeah, okay, that's a perfect assumption. Yeah, sorry, that's a very, very good question. So yes, in principle, you cannot go this to infinity because now it depends on like what's the mean path of the photon, if it's going to be rescattered or like reabsorbed. So yeah, this is just a geometrical argument here, Paolo, for the labeling of the photons. This now, the fact that you will see them n=2, n=3 will depend on material. Will depend on the properties of the plasma or if the photon gets absorbed. Yeah, that's a very good question.
So related to Paulo's question, have people tried to quantify how much the n larger than 1?
Yes, I think one of my collaborators, Alek Lubchaska,
demagnified.
he also make an argument like, yeah, you cannot go up to infinity because now the magnification will be smaller to something that is not physically valid. But now, for the best simulation state of the art of plasma that you know, then it depends on which frequency you are observing. So we know that at the frequencies that the black hole, that IPHT is currently observing, for most of the simulations, you can see up to like n=6 people have seen and something like that, yeah. But then it's very challenging to resolve. Okay, going back to this discussion, the photon shell and this image, like this is what I'm telling you, and this is the key point. Whatever we see in a black hole image depends on 2 things, the astrophysics and the gravity behind it. And the gravity sector is arguably simpler to describe because it just needs these 3 parameters which will depend on the black hole parameters, mass, spin, and inclination of the observer, the geometry. If there are charge, in principle, there will be a charge here. Now, these guys depend on the spin, as I was mentioning. This guy depends mostly on the mass. So the collection and the image that we hopefully will observe, if we have let's say if we have a perfect telescope, will look like something like this. And in this context, what Daniel was alluding this morning as the critical curve or the black hole shadow, in this language is n=infinity. So in principle, it's a theoretical curve that we do not observe because by definition are photons that stay there forever and ever. And that's what we get, okay? So what is remarkable here is that, and Daniel already went through this, is that n equal 2, n equal 3, they are fairly insensitive of whatever was happening around the black hole. And that's why we want to target those photons. So for the remainder of the talk, I'm gonna focus on two things that we can do. The first one will be about this time delay, these echoes, because it doesn't matter what you have. You can put a dragon, you can put Daniel with a flashlight around a black hole. We should be able to see echoes of whatever that emission is. I don't care what it is. Now, for the second part of the talk, which is going to be significantly faster, is going to be about these two guys. And then, as Daniel was mentioning, there is something, a collaboration that's it's happening at the moment. We are proposing an experiment, the Black Hole Explorer, which is going to put an extra node, another telescope, radio telescope, somewhere in space. That's going to allow us to go through this higher, finer resolution or higher resolution in this sort of images. Okay. So let me start with the time echoes. And again, if my background is very different from yours, so please let me know if anything is not clear here. But in principle, there is something called light curves, that is having a black hole movie with just one single pixel. If you take your telescope, let's say this projector, I have a telescope, I just want to count the whole flux as a function of time for my whole telescope, and this is a light curve. So the IPhT have measured this for Sagittarius A star, and this is Sagittarius A star light curve. So just how much in a particular frequency, how much density measured in Jansky as a function of time, and I have converted the time here, assuming a fiducial mass for the black hole. But this is it. Okay, based on the discussion of the previous slide, I told you in this light curve, and people have been expecting this for decades, because of the properties of the Kerr solution, there should be an echo. So if something is happening at the black hole at some particular time, you see the direct thingy, but also you should see the same thing over 16-ish m later. So what people have been doing is like computing the autocorrelation of these light curves. So the autocorrelation will be basically, if we want just to have an idea, take this time series and then start shifting it and look where the taus at a particular shift will happen. Now, this is what you get when you compute this. And then there is here an acronym, because computing the autocorrelation of data that's not evenly sampled and actually has gaps is quite challenging. So you can compute this thing. And then you don't see anything. And people have reported negatively that there is no echoes in the signal. Now the question is why? In principle, this observable should be the easiest one. You don't need to resolve the source, just collect the light and then just find these echoes. People have been looking, there is, in this paper by the IPhT collaboration, the most recent, they report there is no signal for anything interesting related to a photon ring around this 15M. Now you can argue it's because the data is not quite good, then you can do a prediction for Gaussian processes, then you can predict with a model what would be the light in the middle here, and then you can do the same things, same result. So it seems the question is, where are the echoes and delays? In principle, this should be one of the easiest observables we can go after. And as I said, it's going to tell us about things about the black hole. It just depends on how much it took. People have not been able to find this thing. Now, we recently developed a set of tools that allow us to, yes? Yes? Oh, good.
No. What is the shape of this curve telling us at all? I mean, why is it oscillating? Why is it going down slightly? Or
yeah, because of the fluctuation, there are many things happening here. So you have a dynamical system, you have plasma. The plasma is varying, so light that you have around. That's the thing that is causing the structure.
So there seems to be some periodicity, quasi-periodicity. Is that just?
Yeah, no, it's, oh, sorry, because of the gaps or something?
No, the fact that it sort of seems to be going up.
Oh, yeah, well, in principle, you have a mean flux. You have now there are some magneto-rotating instabilities, and then the plasma have some time scales also.
So there's like 3 oscillations on this curve.
Yeah, well,
plasma time scale.
Yeah, that's hard. I don't know necessarily what this will mean, but then yes, in principle, you should is properties of the source.
And also, is it true that it's going down on
no,
average,
so
or
just
not really?
this is an excellent question. So what we're seeing here, it looks like a lot of M's. This is just 8 hours of observations. So now if you put the rest, it will just go back. So what they will, this is an oscillation around a mean in principle. So yeah, you have a source that is fluctuating, and it's because of the plasma is fluctuating.
So it's around some constant.
Yes,
That.
and then you have the
Oh,
fluctuations.
thanks.
Thank you. That's a very good thing.
So that access was 8 hours.
Yeah, roughly yes.
I was estimating it was it's 4 million solar masses. That's like crossing time of let's see, something like 40 seconds. Is
To like
crossing
20
time.
seconds. Yeah, you are.
1600 times 40 seconds is rather more than 8 hours. Okay.
Yeah. Yeah, so in principle, yeah, you like in Sagittarius star, I think like 1M is like roughly 20 seconds if you want to go back to this thing. So yeah, in principle, we should see many of things. So you should be able to see this out of the correlation. And again, and thank you again for this question because it reminded me of something I didn't mention. What I'm going to show you in the next slides is not just for IPHT type of observation. People have been trying to look for these observables in X-rays, in any other electromagnetic sector, because it's a property of the black hole. Cool. Now, what are these echoes? So we have, as I was alluding before, let me address this question with some tools that we developed recently, and it's a way to treat this all astrophysics that we don't know, but then put it in a different setup. So what I'm going to show you is a simulation that is actually solving this stochastic partial differential equation. What we want to get is a Gaussian random field that is controlled by a covariance where I can prescribe by hand any correlation I want. And then it's a partial differential equation, so every time we solve numerically this equation, I get a new realization of the Gaussian field. So what is important here is that you can have here a sort of like, in this case, I'm going to show you 2D simulations that evolve in time, so 2 plus 1, of emission that I'm going to put in an equatorial plane. So there is no GR, and there is also no astrophysics. And I can prescribe whatever I want in this matrix, because I want to know. And this will be my proxy for the astrophysics, okay? So you solve that equation, and this is what this was done by David Lee and Charles Gamy, and then you produce this sort of thing. The black hole and then the profile is something that you just do ad hoc. But then the idea is that these correlations in space and now how this evolve in time, you can control it. These simulations are actually quite cheap to perform. Now what you can do is, okay, this is going to be my intensity in the equatorial plane. Now I put all the GR effects and I produce an image. And now we develop the framework for this. It's called adaptive analytical ray tracing because everything is done analytically and you can do it in a personal laptop and you compute images that look like this. Now, again, there is no astrophysics here. You put all the GR here. And then again, n equals 0 looks a lot like here. N equal 1, demagnify, rotate the time delay, n equal 2. And this is what Daniel was saying. Now here you can define sort of like a diameter. In this is actually ill-posed, as Daniel mentioned. What's the diameter here is actually not clear, as opposed here. You can get a characteristic timescale. Okay, so now we have this technique to produce black hole images, and I can prescribe by hand the correlations I want. And I can go about the question you were saying. What is this? I can control everything. So for example, let me start with a correlation in time where I put 1.5. This is for the emission, for the plasma, for the astrophysics. And let me put these two spatial correlations. These don't matter because when we compute the light curve, I integrate over the space, okay? And then I can compute my light curve. This is the animation of that. Again, no astrophysics, no GR, just purely this emission profile, and you get a light curve. And now I know, because I put it by hand, the correlation, the temporal correlation is 1.5 m. This is the light curve. You do this, you compute the autocorrelation, and boom. It makes sort of sense. Around 1.5, you lose half the correlation, then it decays exponentially. This is a realization. This is coming from a stochastic partial differential equation. So whenever you solve this equation, you should get a new realization. So this is done numerically. This follows all the expectations we have. We have an analytical prediction for that. And then numerically, we can solve it. Okay. Again, no astrophysics, no GR. But it makes sense. I can have an analytical prediction for that. So now let's put a black hole here with certain spin and observe at a particular location. And now I compute the autocorrelation and I get this. Whoa, the bump. This is quite expected. So you have, again, the correlation that we can prescribe is this. The relativistic part is bringing this term, okay? Now for this one, we also have in our paper that came up on Friday, this analytical prediction for that, and now you have this. Cool. This depends, I told you, on the delta, on the tau, and then this will depend on the other parameters, but the other parameters are subdominant. So here you will just have the correlation like that. Awesome. This, now if you recall from data, looks quite different from how Sagittarius A star actually looks. Now, you might notice I put this time correlation of those simulations to be 1.5. What if we use something that is more physical? What if the flow is evolving temporally Keplerian-like, it follows a sort of Keplerian profile, 2 pi divided by the Keplerian frequency. Then you get something like this. So when we did this, so we first did this, okay, nice, we have an analytical prediction. When you do this thing, we cannot compute an analytical prediction for a particular scenario that we put here, because now this generates inhomogeneous and isotropic Gaussian random fields, so the statistics gets really complicated, but you immediately notice something like that. Now this is simulation. This is not Sagittarius A star. So I can actually sample this as much as I want, take the derivative, put a high-pass filter, compute the autocorrelation, everything, and then you don't see anything around 15. So we were super puzzled. Okay, now we have the simulation, we can control everything. There are no echoes. And this arguably is the best scenario, because I control everything here. I can sample this as much as I want. The echoes are not there. Now you can have a model. Now you can assume a sort of astrophysics and fit an effective correlation time for this astrophysics. And then it's 54M. So these numbers right now look cryptic. Let me go to my next slide to explain what's happening here. So the model that we came up for the autocorrelation of the light curves will have a term that is everything that just depends on the plasma or your astrophysics. And then there will be this relativistic correction, and this is the important part. It depends on the plasma as well as on the black hole parameters. And it's extremely sensitive to this ratio. Whatever is your effective correlation in the plasma versus the one that the black hole is dictating. When this number is small, that means that the correlation of the plasma is small in comparison to the time correlation the black hole is imprinting, then you have a bump. And this actually makes sense. You will measure something, the plasma is not correlated anymore, and then the black hole appears. And now this, you can see in our paper, the model for the details. What happens is like you start increasing this number, and then you don't see a bump, you see an excess. And as soon as you go certain threshold, there's nothing. So to show you an animation of how, again, if you want to know the model, you can go and see the details in the paper. It's actually not quite complicated model, but I don't want to go into the details here. The point is that this second relativistic term I'm plotting here, this is how it's evolving whenever you change this. So it goes to a bump, and then it's just adding a background. So this explains why people in X-ray data, IPHT type of millimetric observables, you cannot see. So the echo is actually quite hard to get from this. It's just lost. The plasma is actually eating like this contribution. So what you in a way to physically understand this is like the plasma is actually eating this part of the contribution of the black hole. So this is why we argue people have not been able to observe this, and we provide a proof in our paper. Okay, so the summary of this part is that this is how data looks. People, it doesn't matter how you sample or this is what we argue, because if you put something that is Keplerian-like, your sources might not be to be Keplerian, but this is a little bit physical. This will always satisfy this, that we are in this regime. So we are in the regime where this observable actually is not helping us, because the correlation of the plasma that we need to have light is much, much larger than the correlation of the black hole. So that's one of the three concepts. Okay, and then we provide a model for this thing. And as I said, like our paper came out on Friday, it's just 4 pages. I invited you to see for the details of the model. Okay, this was, I argued at the beginning, 3 observables. Gamma, this is the magnification, delta, rotation in the images, and time delays. So with time delays, it's actually quite hard. We show for autocorrelations, if this doesn't matter on the model astrophysical. It's whenever you can have effective time scale for the plasma, it doesn't matter what plasma you put, this is always going to be true for the autocorrelations. So this is very generical. Okay, questions so far? Yes, Aaron?
Does this tell you something about the astrophysics?
Yes. So now again, this is, if you do, when you compute just the, let's say you start with the Keplerian flow in my statistical approach, you compute the autocorrelation, then the one that you will infer, let's say, if you use the Keplerian, is like 88 m. When you put the black hole, this guy goes to 54. So in some sense, if you know the astrophysics, then you will know there is a discrepancy because there is a black hole. But again, this is just only if and only you know the astrophysics. So yeah, the black hole is present here, but it's not manifested in a bump as people were expecting. And we provide the explanation for
Thanks.
that. Cool. Okay. Now, in the next 8 minutes or so, I'm going faster than this just to circle back to what Daniel was mentioning. Now, let's go back to these three quantities that I mentioned. So this one is actually quite hard. We might want to actually to spatially resolve. And that was what Daniel was mentioning this morning. So let's go after these two other observables that are in the image domain. And for that, my contribution in addition to what Daniel was mentioning is that everything that was done, so far for the observables that Daniel mentioned are when you assume you have a perfect time average image. But when we measure stuff, it will have this sort of dynamics. And it's hard to see here, not because of the light, don't worry, but it's like there will be black hole mimickers. It's actually, if I told you, okay, there is a photon ring here, you don't know exactly where to measure, this is changing as a function of time. So everything that has been done in this for images was assuming that you perfect average, and that if you average this, then you have this guy, you have perfect sequel, n equal 2, and then n equal, and so on and so forth. So what I'm going to talk about in the following 5 minutes is just that we put this into a machinery that's able to address, okay, in practice, how easy or challenging this is to measure. Okay, and then again, just to recap one thing that Daniel measured, if you have a source, this is just to give you a sense, not to you have two telescopes. This is more or less how BLVI will work. You're observing a source. There will be a delay. This has nothing to do with the time delay I just mentioned before. It's just the separation of the telescopes. Let's call this temporal difference T1. But then the point is that this telescope measures an electric field in those radio dishes. So the observable that Daniel was mentioning is the correlation, has nothing to do with my previous correlation, but it's just the correlation of, in your telescope, you measure the electric field, and then you can, you correlate them, and you measure something that is the visibility amplitude. So this is a fact. So what, as Daniel was saying, what the telescope observe is something is in the Fourier domain. And then the point is that you can prove that if you have an image, the visibility in the sky, the 2D image in the sky, is just, you have your best theory of gravity, your first astrophysics, just Fourier transform, and that's what the telescope will observe. So that's why Daniel was actually mentioning this quite carefully, because we are observing in the Fourier domain. So again, just to clarify, you will have a projected separability here, and then observational wavelength. So choose which telescope you're going to use, I don't know, 245 gigahertz, 345, or it doesn't matter. Choose the separation, and that will tell you where in Fourier space you are. So if we fix the observation length, how can we go to spatially resolve better? That's why we need to go to space. So this is the kind of explanation why we want to resolve that. And this connects to what Daniel said, is because the black hole image is kind of forgetting about the astrophysics. It becomes less and less dependent, and that's the tricky, and that's the important part here. So just to summarize again, you will see something like that, and if we have access to all these photons, but we don't, then this is how n equal 2 will look like. It's a big tunnel, it has certain depth, and then if you have a ring in the image domain, it will be a vessel 2 decaying like this. And then the other ring, and this is the interesting part, will just appear. This is how n equal 1 it look, and then n equal 2. Of course, what we observe is the black thing. So that's why it makes sense to go after like all of these things, because in the signal is always present n equal 2, n equal 1, even at the short baselines fixing the frequency where the IPHT is observing. So that's why people have been trying to also look in the data, because it's somewhere there. But the point is that was what Daniel was saying. You want to go to a regime where one of these dominates, because it's forgetting the thing. Okay, so the task is, and then you can see there's going to be these regions where there should be color here. This part is dominated by n equal 1. There could be transitions here between n equal 1 and n equal 2, another transition here, and you want to measure the circlips that Daniel mentioned. The circlips, as Daniel mentioned this morning, for n equal 2, if you can, well, in this case, if you have roughly $1 billion, you will be able to go to n equal 2. But we are asking NASA a factor order less of magnitude of money, so we cannot get to n equal 2, we need to go to n equal 1. So this is like something between Earth and the Moon put a telescope, which is still quite expensive. N equal 1, this formula holds to percent level. So going back to Paolo's question, if you go here, it's sub-percent, as Daniel was mentioned, 0.04. But if you go to n equal 1, it depends on the astrophysics a little bit. Now it's not a thin disk, it's a thick, but the thickness is ratio like that. But then we show in this paper also, for many models, astrophysical models, because now we have to care about the astrophysics, it is percent level good. So it's not sub-percent, but now it's still quite good. And we show that for n equal 1. So that's the task. This is something that Daniel mentioned. So now the point is that you can go choose your best window and then try to measure the diameter. But now what we're doing is like you can put, this is you choose one of these diameters, you want to fit this functional form and then see if it holds what GR is saying or this type of thing. And this is the circlips. Connecting to one of the other questions, if you are able to measure this with very good details, 0 and the 90, you will have an asymmetry. And the asymmetry tells you something about the spin and the inclination. So in principle, you get information, but as Daniel was saying, so far we are not super clear how to infer spin. There are many ways like that. So what we did is we put instrumental noise and we put the fluctuations, and we noticed that in principle you can do this, but you need to average for certain snapshots. And it's actually quite hard, and this connects to what Paolo also asked, if you're just measuring the parallel or the perpendicular diameter, because I want to know the symmetry of the ring. Sometimes, because of the noise, instrumental, or the fluctuations, the circlips gives you a good value somewhere else. So I know this is truth because I can get it from the critical curve in my simulations, but actually when you do the data analysis, you start finding other peaks. And the reason is because you can be at a place you are observing for a particular profile, n equal 1, where you are at a transition. So this is quite challenging because we don't know the transition where the direct image to the first photon ring is being dominated. So it's just to put this noise. Now you start averaging, and then these two peaks appear. But if you go to a place where n equal 1 dominates, and remember, this is not controlled by us. This is just the black hole, certain astrophysics around it, and now the question is, we should be lucky, and then that we are observing in a place that is not transition, otherwise we have to do very sophisticated stuff. But in principle, we can always do. If you are in a place where just n equal 1 is dominated, you will measure very nicely a diameter, and from this diameter in principle infer spin and the properties of the black hole. So yes, it holds even if you put instrumental noise, it holds even if you put fluctuations, but it's actually a little bit challenging. You just need to average a lot. So the summary to this part is even these observables that Daniel measured, they still hold when you consider astrophysical fluctuations and when you consider noise, but it's not as simple as that. So now if your theory just differs by a little bit of GR, then again, it's gonna be quite challenging to measure this in an actual observation, okay? So you can always define an interferometric diameter, you can always measure this diameter, but as I said, it's going to be very challenging. Now, if you have more information, so for example, for Sagittarius A star, the animation that Helvi showed of these S2 stars, you can infer the mass quite well. So we know the mass of Sagittarius A star quite well. So that could be a prior for us to use from another observable. But in M87, we don't know the mass that well. The mass estimates actually is a factor of 2, which is quite a lot. But we know the inclination because it has a jet. So we know the inclination quite well. Whereas in Sagittarius A star, we know the mass, we don't know the inclination. So that's how nature works. So in principle, we need to work and have a multi-messenger approach from that. Okay, and with that, I think I'm good to take some questions for this summary. Thank you.
Questions?
So this plot that you showed before, the one with n equal 1, n equal 2, few slides before, yeah, this one here on the right, for example.
Sorry, I went too far.
Yeah, this one here. So does it depend on the spin and inclination angle?
Yes. So the way this ringing will happen, because it depends on the parameters of the black hole. So the diameter will tell you. So what you're seeing here is a particular cut. You think about you have your you have the image of the black hole, and now you are observing it with a telescope that's rotating. So you have Earth here, an observer, and then the dish. It will give you a projection, but now this is moving, so now you at some point get another projection in the image. So this is something like that. So this will be, let's say in this context, phi equal 10 degrees, let's say. So yes, this diameter that you're seeing, Paolo, depends on the spin and so on. And now it gets more complicated the closer you go, because of the decomposition of the image. It will also depend on the plasma, because you will have black hole, photon mimickers and stuff like that.
So the hierarchy between different ends, does that depend on the spin as well?
Yeah.
Right.
Yes. Yes. In some sense, where this happens, yes, it depends
the
on that.
transition
Yes,
when it
yes.
does. Okay. I see.
But it's more sensitive to the astrophysics. That's the important part, the hierarchy. Yes.
In the visibility function, there is 1 over square root of u divergence, 1 over square root of the length. Can you explain that?
I guess. Well, this is, I don't have it here, but I think you're talking about, you have this dependence of 1 over square root of u, and then your observable here. Yeah, this is because you are expanding, assuming that you have a narrow ring. So this is completely regular for small baselines. So these observables, we're assuming you can expand this expression as 1 over u. So more or less what you want to see is that it has a mild 1 over u decay. But it's not because it's irregular, because this expression was derived when you assume u large.
What's the scale that separates the two regimes?
So it's both. So it depends. The scale that separates that thing is going to depend on the astrophysical profile where this is happening. So for certain profile. So a way to think about this again, if this is your image and you have narrow disks, they will survive the longer. This happens. So depending on your width, this is how much you will have here. So if you have very thin disk, the n equals 0 will survive for longer than equal 1. This is the next image. So it depends on the width of the disk, and that depends a little bit on the astrophysics, of course, because if you have something that peaks very close to a particular radius, or it doesn't decay that much. So that's why it depends on both things.
So what I'm hearing is that n equals 1 is still going to be very hard to get data out of. It's really n equals 2 is the kind of gold standard.
So we're very optimistic, and that's the point. Like with this, all of these are our assumptions, and also it seems to still hold. So just to clarify, one of my conclusions is that n equal 1 is the one that our pocket is allowing in the following 10 years. And even in those cases with the Black Hole Explorer, we are quite optimistic you can get a shape. But it's not, again, percent level as Daniel was saying. You can get something that is percent level good. And that means that we hopefully can be, I don't want to quote a number, but in some sense measure the spin well. And that well, I'm being recorded, so I'm not going to tell it here. I can tell you over the break. But in principle, we should be able to measure this asymmetry. So yeah. Now, one of the key points here is, Nick, is if it's not good, we just need to take more data, because the average is what we need. We just go over and over, and then maybe get clever at some point. This analysis was
to get to n equals 2. What are we talking about? Putting it at the Lagrange point of the Earth?
Something
or
like that. Something like that. Yes.
That's the $1 billion.
Yeah, that's
And do you think that with the n equal 1, which is what your pockets allow you to probably get in the next 10 years, would that be enough to tell apart different space-times of the type that Daniel was mentioning?
No,
this
and
morning?
then I guess I have some backup slides. So for that's something we explore. As I was mentioned, for n equal 2 in our theories of gravity, Daniel's paper he mentioned this morning assess that. They are quite similar. For n equal 1 with Aaron, we study this. If you measure something, then you can have your theory and ask yourself, is this allowed or disallowed, like that? But then the point is that these are kind of funky space-times. So in some sense, you can always perform. So pick your favorite theory. The Black Hole Explorer give you some data, and then you can compute just from first principles. My theory allows to have n equal 1 emission within this region. So yeah, you can exclude certain theories, but actually not that strong.
Mm-hmm. Okay, thanks.
Yeah. And if I may, yes. If I may, I just want to, just because of the other questions, the material I want to mention at some point is that Yes, this is n equal. N equal, it goes to 2% level. Then you can really constrain. But then, as Daniel showed in this paper with all of the many other theories can also predict this thing. So it's actually like that. And then I guess I just because of the context, and it just if people want to ask me this about this over the coffee break, is that if you have another space-time higher dimensions, I still have like 3 minutes, right? Just to so what I show you here, what about like higher dimensions? And then just because connecting what we're saying. So in principle, there is no astrophysical evidence for higher dimensions so far. But they are quite interesting, right? So you know they exist, and now one of the key properties that seems to be genetic from higher dimensions is that this story that I tell you about the trapping is actually not unstable like in GR. It's actually stable. So someone you were mentioning, okay, then something will build up here. So there are some simulations in backgrounds that allow for trapping, and this is just to really flash out this sort of simulations, where you can have a scalar in a background that allows for stable trapping. And you just put a non-linearity here, so this is just a scalar field in a space-time that allows for trapping. And actually, things don't build up because it's actually quite hard. Even if you have the trapping, there is some leakage out of this potential. And if you put a black hole, it's leakage because of infinity. The wave will decay, but also they will go into the horizon. So even if you have stable trapping, it's going to be very, very challenging to find these instabilities. And this connects exactly with the photon ring. Even if you have stable trapping in higher dimensional black holes, it has to be very effective. And here, with this collaboration with Gabriele Benomio, Andrew Sullivan, and Franz Pretorius, we are showing, like, here we have a sort of like simple model phenomenological where we can trap stuff. Linear versus non-linear is quite similar. And then you have trapping. Some things grow, but then this thing doesn't necessarily seems to be unstable to something. So just to clarify one of the things that Nick was mentioning, yeah, even if you have stable trapping, photons will be there, but then it's not like a bomb because these systems will generically be dissipative.
So what do you mean it has to be the trapping has to be very effective in order to see what?
So I'm not an expert on this, so maybe Helvi can comment more of this or even Roberto, but some people have shown instabilities in ADS, spherically symmetry. And then, okay, you have the boundary, so the boundary is actually always pumping it up. If you think about asymptotically flat spacetimes, and now you have something, let's say a black string or something like that, and you have stable orbits that are allowed, then you put something, it is still this leakage. So you can write out about a potential. So energy is conserved in these systems. So you have sort of like what I'm showing here is this animation. You start with everything, but at some point your stable, the bottom of your potential is kind of here, but you're always leaving the system to asymptotic. So energy is being conserved. Everything is like that. You can actually, and this in our paper, we're showing a Kolmogorov cascade of energies to high frequencies. But now the question is, can this create a black hole or something like that? It seems that no, because it's not good as in ADS. You can concentrate everything because of the boundaries. But then as soon as you are not in spherically symmetry, you can have something, but then the energy is just shuffling and you are keep dissipating and then just moves on. We can talk about this more on the break. Yeah.
What he's saying is that what the fuzzball instabilities that people say will lead to black holes actually don't.
I got that.
Yeah, that's why I also mentioned this thing.
Does some fluctuation in angle?
Yes. So you start with, this is a spherically symmetrically background, but with an axial symmetrical perturbation, L equal 1, L equal 2, just put your favorite. Energy will propagate to higher L's, but then energy is not concentrated because it's just shuffling around the solution and so something like that. So yeah, this was something I just added this morning just because of this discussion. So I'm happy to also talk about this because this applies to boson stars and stuff like this. So just to, my point here is that even if you have stable trapping, it doesn't necessarily lead you to smoking gun things. Like you can have something that is still stable trapping, but it has to just, it's very complicated to keep it trapped. Even if it's stable, then it will just dissipate.
Maybe maybe a last question.
I want to be provocative in that part, yes.
Sorry, I can't resist a clarification. Just to clarify here, you have both a horizon.
No, this one is just, this doesn't even have a black hole. This simulation I'm showing you here.
Okay, so there's no horizon in this.
Yes, there's no horizon.
But you have flat asymptotics rather than an ADS-like
Correct.
box. Have you simulated it for ADS with
No.
the same setup?
No, but
And
there
you-
are some papers that 10 years or 12, 14 years where they have studied this sort of phenomena in ADS. And that's what in spherically symmetry it leads to an instability.
Right, because then I would be cautious about claiming that this resolves
Yeah.
what has been discussed in microstate geometries. Where
Yeah,
they
no,
have,
it hasn't. Yeah. That's,
ADS-like
that, what
threads.
Daniel said is a conjecture, actually. Right? Yeah.
Okay.
Is the energy leaking out to infinity, or is it just slopping around?
No, it
in
goes
the
to
trap?
infinity, and
It's-
then yeah.
So is it tunneling, or is it?
Yeah, it tunnels. Like whenever you write, you kind of write these sort of equations. Like just think about the geodesics and stuff. In the high frequency limit, you can write like a sort of Schrodinger type of equation with a potential, and it will just tunnel. Yeah.
Wow.
And I talk more about photon rings because that's what I was asked. But I'm happy to talk about more of this, also this stuff. Okay.
Well, maybe that's a good segue into the coffee break. So let's thank Alejandro again.
Thank you.